this video, we're going to analyze heating curves for various substances. So a heating curve is basically a graph of the temperature of a substance versus the amount of heat that is added to that substance. Now, as we add heat to a substance, we would of course expect the temperature of that substance to increase, maybe in a linear manner, something like this. And that's true to some extent, but heating curves are a little bit more complicated than that. To illustrate that, let's take a look at the heating curve for water. Since we're all familiar with water, we know that at 1 atmosphere, water has a normal boiling point of 100 Celsius and it has a normal melting point of 0 Celsius. So let's analyze the heating curve for water. Let's say that we start off down here at negative 40 degrees Celsius. So of course our water would be in the solid phase or ice. And as we take our ice and we begin to add heat, so as we're adding heat, the temperature of that substance, of our ice, begins to increase in a linear manner. And it does that up until we get to the melting point. At the melting point, we can continue to add heat, but something interesting happens. As we add heat, our temperature remains constant. So we're adding heat, but the heat is no longer going into increasing the kinetic energy of the molecules and therefore the temperature of the substance. Our heat is now being used to do work. It's being used to disrupt the intermolecular forces in the water molecules, between the water molecules, and convert our solid into our liquid phase. So remember, anytime we need to break intermolecular forces or break chemical bonds, heat is always required. So that heat's being used to break those bonds, and our temperature remains constant. Now, once all of our ice has been converted into the liquid phase, we can continue to add a heat, and our temperature will now begin to increase again in a linear manner. So as we add our heat, our temperature once again increases until we get to the boiling point. Again, the same thing happens once we get to this phase change. We continue to add heat, but our temperature remains constant. That heat, again, is being used to do work. It's being used to disrupt the intermolecular forces between the water molecules and convert our liquid water into the gaseous state. So once all of the water has been converted from the liquid to the gas phase, and again, that takes a certain amount of energy, we continue to add heat and our temperature will once again increase. So this is a general structure for a heating curve. This of course applies to water, but it also applies to other pure substances. Ammonia, methanol, ethanol would have heating curves similar to this. Of course, the boiling point and the melting point for those substances would be different. Now, a couple of terms that we want to familiarize ourselves with are the enthalpy of fusion and the enthalpy of vaporization. The enthalpy of fusion is the amount of energy required to overcome enough intermolecular forces to convert a substance from the solid to the liquid phase. The units are kilojoules per mole. The enthalpy of vaporization, the amount of energy required to overcome enough intermolecular forces to convert a substance from the liquid to the gas phase. So if we look back at our heating curve, our enthalpy of fusion is right here. That's the amount of energy that it takes to convert our substance from the solid to the liquid phase. And our temperature remains constant during that phase change. So basically our enthalpy of fusion is the amount of energy it takes to undergo the phase change from solid to liquid. The phase change from liquid to gas requires a certain amount of energy or heat as well. That amount of heat is our delta H of vaporization. So notice that our delta H of fusion is smaller than our delta H of vaporization. And this is true for a lot of substances. Here's some heats of fusion and vaporization for a number of different substances, ammonia, benzene, ethanol, etc. Notice that in all of these, our delta H of fusion and vaporization, the vaporization is always larger. So why do you think that is? Pause this video for just a second and think about that. Well, when we're converting from the liquid to the gas phase, we have to break a lot more intermolecular forces. Remember, to get into the gas phase, all of our intermolecular forces must be overcome. From the solid to the liquid phase, we still keep a lot of those intermolecular forces intact. And so since we have to break a lot more intermolecular forces to get into the gas phase, it requires a lot more energy per mole. So these values are almost always larger than the delta H of fusion. And again, pay attention to your units, as we'll see those are very important. So here's a couple of questions related to heating curves. Pause the video, take a minute, and answer these. Pick the choice or choices that are most correct for each one of these. Okay. So the flat lines on heating curves, well, the temperature does not change, so it represents a constant temperature, and it also represents a change of state or change of phase. The slope lines, that's where we have a temperature change, so we're not undergoing a phase change during those sloped regions on the heating curves. So we also want to be able to perform some mathematical calculations so we can calculate how much energy is required to convert a substance or to increase the temperature of a substance from one temp to another. To figure out how much energy is required to increase the temperature of a substance, we would use this formula, Q equals Cm delta T. In this formula, Q is the energy in joules, so this would be the energy required or released, depending on which way you're going. C is the specific heat of a substance we're talking about. Remember, specific heat is the amount of heat it takes to increase the temperature of 1 gram of a substance by 1 degree Celsius. Every substance, every phase of a substance also has its own unique specific heat. M is the mass in grams. Of course, the more mass of a substance you have, the more heat it's going to take to increase the temperature. And delta T is the temperature change, temperature final minus temperature initial. So let's take a look at a problem where we might use this to kind of illustrate how we would use this formula. Calculate the amount of heat required to heat 7.50 grams of water from 25.3 degrees Celsius to 75.8 degrees Celsius, and you're given the specific heat of water. Pause the video and give this problem a try. Okay, so how much heat does it take? Well, we would use our formula. We would use the specific heat of water, which was given, times the mass of water in grams, times the change in temp, final minus initial. Notice that my grams will cancel, my units of degrees Celsius will cancel, and I'll end up with my heat or energy in joules. So to 3 significant figures, it would require 1,580 joules to increase the temperature of 7.50 grams of water from 25.3 to 75.8 degrees Celsius. So that's how much heat it would require. Now let's take a look at this problem. This one's a little more complicated. Calculate the amount of heat required to completely convert 5 grams of water from 90 degrees to the gas phase at 110 degrees Celsius. So we're starting out with liquid water at 90 Celsius, and we're converting it into gaseous water, or water vapor, at 110 degrees. You're given the specific heat of water vapor. Now you may also need some other numbers, so you might need to go back in the video and pick up a couple of numbers. I'm not going to tell you what they are. But essentially, if we look at our heating curve, here's what the problem is asking. We have 5 grams of water at 90 degrees Celsius, so right here, and we want to convert that into water or increase the temperature of that water to 110 degrees Celsius. So that would be right about here. So we want to calculate how much heat it takes to get from this point to this point. And I'll give you a little hint. We have to do this problem in 3 steps. We have to determine the amount of heat to get from 90 degrees to where we start the phase change right in here, and then the amount of heat it takes to completely convert that water from liquid to gas. So this would be another step here. And then finally, we want to convert that, which is now gaseous water, vapor, from 100 degrees to 110 degrees. So we would calculate these three steps and add them together. Okay. So again, pause the video. Again, like I mentioned before, you may need a couple of other numbers. Pause the video, give it a try, and then take a look at the solution when you're done. Okay. So as we mentioned, we want to do this in three steps. I'm going to calculate the amount of heat, Q, to get from 90 degrees Celsius to 100 degrees in the liquid phase. I then want to calculate the amount of heat it takes to undergo the phase change. I'll call that Q of vaporization. And then finally, I want to calculate the amount of heat, Q, it takes to get the steam of the water vapor from 100 to 110 degrees. Add those three together, and that gives me my total heat required. So let's do this one first. Q from 90 to 100. We would use our formula, C times M, the mass, times the delta T. So the specific heat of water, we gave that to you earlier, times the mass of the water, in this case 5 grams, times the change in temp. From 90 to 100, that's where we begin our phase change. So if I plug these numbers in, I get 208.95 joules. This will have 3 sig figs. I don't want to round it until my very last step, so I've just underlined the 8 as my last significant digit here. So this is the amount of heat required. One thing I should mention here, the Q values here are positive because we're requiring or adding heat. If we were going the other way from 100 down to 90, heat would be released and we would have a negative Q. So you can use these heating curves to go up or down on the heating curve. Okay. So now let's look at our second value. This isn't the final answer. We now have to calculate the Q for vaporization. To do this, I have to take the 5 grams of water and I have to convert it to moles. I have to do that because the enthalpy of vaporization is 40.67 kilojoules per mole of water. So I've got to convert my grams into moles. Very important to pay attention to your units. Therefore, my grams cancel, my units of moles cancel, and I end up with units of kilojoules. So here, again, I don't have to take into account the temperature since it's constant. So to get the Q of vaporization, I basically have to just take the moles of my substance and multiply that times my, excuse my writing here, delta H of, in this case, vaporization. Now, if you're given grams, you can convert that into moles. So that is delta H of vaporization. So here, now I've also gone ahead and converted that into joules. So all of our units will be the same. I've accounted for sig figs, but I don't want to round yet. Okay. Finally, I want to get the last number that I need here, which is my Q, the amount of heat it takes to get from 100 to 110. In this case, we're talking here about water vapor. So I need to take the specific heat of water vapor or steam times the mass times my change in temp, final minus initial. And again, my units cancel. I'll end up with joules, and I get 101 joules. So now I just add those three numbers together. I add the Q from 90 to 100 in the liquid phase, plus the Q, how much heat it takes to convert my 5 grams from liquid to steam to gas at constant temp, plus the amount of heat it takes to get the steam from 100 to 110. Add all those together, and when I round that to the correct number of sig figs, I get 11,600 and units of joules. And this is a positive value because I'm adding heat. If we were going the other way, we would end up with a negative value because heat would be released. So practice a few more of these heating curve problems and be sure you understand these calculations and be sure that you can repeat these for any substance that you are asked.